Okay, this is going to be a very short presentation on filters because we've already talked about filters so much, but there are a couple things that we should just direct towards filters instead of filters feeding into something else. So I didn't even write any notes down for this. We're just going to go through it real quick. So filters are devices, either mechanical, electrical, or electrical or software that removes unwanted frequencies from a desired signal. It's an arrangement of capacitors and resistors in a certain way, and it allows us to eliminate frequencies gradually and in both directions. Unwanted frequencies are called artifacts. So when we're looking at the EEG, if we were just to have no filters, it would be a huge black block because that's all the frequencies, virtually probably all of them coming from all sorts of sources. So we have to put on these filters so that we can get rid of that and get only the ones that we want to see. There are several filters: anti-aliasing filter, low and high frequency filter, and a notch filter. An anti-aliasing filter is used to minimize the effects of frequency aliasing. This is the waveform distortion created by the data not being sampled fast enough for a digital system by analog equipment. It's reduced but not eliminated by sufficiently filtering the data before it is digitized while still in its analog state. A distortion of waveforms caused by sampling rate different than the output rate is called aliasing. So when we've got some brain waves that are going so fast, but we're not, let's pretend we have a camera and I'm doing something that requires 100 frames per second to catch it, but our camera is so old that it only catches 25, so it only catches certain images of what I do. So there might be where my arm is in one place, and then in the next frame it's in the complete different place because the camera is not able to take enough pictures in a second to capture everything what I'm doing. This is the same thing with aliasing. It's not able to sample the data quickly enough to get the pure waveform. And thus, when we try and digitize it, it looks really weird. This is what wave distortion. So we've got the sleep spindle at the top, 250 samples. You can see it's very dark. It's able to pick up all of those frequencies coming in. And at the very bottom, with 31 and a quarter samples, it's really just waves, smaller waves. It's not, you don't see a whole bunch of those. So this isn't a great picture because it's not very clear. But that top one definitely has thicker spindle waves. You can't really do anything about the anti-aliasing filter. It's done somewhere in the system so that you don't really need to worry about it. But that is what it does. Low frequency filter, also known as the high pass filter. Remember, it allows high frequencies to go through. So anything above this set is what we are allowing in. It establishes the low frequency recording limits. It also controls the rate of the signal's fall. Remember the time constant when we're calibrating our equipment and we have that the calibration signal. This is what controls the rate of a signal's fall time. It also allows the signal tracing to return to the baseline at a speed no lower than its setting. So it's got to go back to the baseline or else it might just go off the screen. If we didn't have these filters and resulting time constants, those waves would travel all over the place. It's similar to how an electrical baseline is set by a reference electrode. These are the low frequency filter settings for PSG. In fact, what I did to memorize this stuff was to put all the settings in order from lowest frequency to highest frequency. So I put all the 0.3s together, and they all started with E. You got EEG, EOG, and EKG. And then Well, before that, you've got respiration. A lot of times, with the frequency filters, we're more worried about the EEG, EOG, EMG, and EKG, because if we want to change how it looks, sometimes that's how we do it. With the respiration, we don't really do that so much. But that's one way that you can remember it. Low frequency filter, when you want to, if you need to change a filter due to sweat artifact or a respiratory artifact, you change the low frequency filter. Why? Well, let's talk about it. Sweat artifact is when the patient's sweating so much that it makes the waves kind of sway up and down. It could even cause artificial or artifactual slow waves or blocking artifact if the pins aren't traveling, if they can't go as far as the wave is pushing them. Also, respiratory artifact. Sometimes where the wires are under the patient, or if they're trapped in another, like under something, that can influence the signal, because as they're trapped on the patient and they're pulled taut against them and they breathe in and out, that wire is moving, so that could cause that. So sweat is slow wave artifact, and respiratory is also slow frequency. So these are low frequency filters. We take out those low frequencies that are artifactual. That's why we use a low frequency filter. Here's an example, let's see. So we're looking at 4 of the same epoch. We have A, B, C, and D. I don't have the specific filters that were set, but I can give you a decent estimate. Figure A appears to be the native signal with just regular 0.3 hertz low frequency filter. It might not have any filter on it at all. But there are a lot of bigger waves that are artifactual from sweat. B shows approximately 1 hertz artifact, or 1 hertz frequency filter. These signals are a little straighter, and they don't meander up and down so much. They have a decent baseline. The voltages do decay over time quicker and don't have as much amplitude as figure A. C appears to have a low frequency filter of like 2 or 3, and those delta waves are much smaller, and the signals themselves are much straighter. And the last one, D, shows really straight tracings with very little deflection. So that looks nice and all, but how do you know when you're actually filtering out proper delta waves that the patient is actually producing? So that's one of the issues you face when setting filters. You face the possibility of changing the trace so much that it's not accurate anymore. So while you're getting rid of the sweat artifact, you may be getting rid of real delta waves. Sweat artifact. First, attempt to eliminate the sweat artifact by all other methods prior to changing the low filter frequency filter. You cool the patient off with fans or air conditioning. Place a towel under the patient's head. You can re-reference the exploring electrodes to unaffected channels. So if they're sweating more so on the right side, that would be the C4. You could re-reference to C3. Or you could try and re-prep the scalp electrodes. You can try that. So what do we use? The high frequency filter or the low pass? It's all the lesser frequencies we're allowing in. And it establishes the upper frequency recording limits of the instrument. It controls the rate of the input signal rise. So when we've got the time constant, when it goes up for the calibration signal, that is the high frequency filter. It allows the signal tracing to reach its peak excursion at no speed higher than its setting. It eliminates unwanted faster signals from being displayed. So the time constant shows you the upper and lower frequency filters and how it affects a 1 volt signal when it comes in. These are the parameters and the settings for high frequency filter settings. And if you're going based off of, I would learn the lows and the highs together. so that you're not confused. So for instance, in the table you might have EKG goes from zero point 0.3 to 70 hertz. EEG is 0.3 to 35 hertz. So is EOG. EMG and snore, I believe, is like 1 to 100 hertz. So I would remember the range instead of just the lower and the upper. High frequency filter, what can we use it for? We can use it to get rid of some of the muscle tension artifact. Muscles contract at a much higher rate than brain waves do. You could also, if you've got a patient that's got one of those things, the devices with a nerve stimulator in their tongue that makes them shoot their tongue out of their face. That's literally how it works. That gives you a lot of artifact, and you can use a high frequency filter to help with that. Muscle tension artifact can be corrected by having the patient move to a different position. Usually that goes away when the patient sleeps. You hold a lot of tension in your face, and you don't even know it. That's why we have RBF, if you know what that is. That's when you forget what your face looks like, and you started squinting or pursing your lips or flexing your eyebrows or something, and you forget that you're just holding that in your face. And that's probably a lot of the times what you're seeing with these dark signals at the beginning of studies. So try and get rid of it before you try and mess around with the frequency filter. I'd probably, if it's not so bad, I might even wait till they fall asleep. So when they fall asleep, usually it looks much better. The cutoff frequency, those are the settings that you're doing. The low frequency filter of 0.35 is the cutoff frequency, although it is never a clean cutoff. Notch filter is the 60 hertz artifact. It's used to eliminate electrical interference, generally from other electrical devices. Charging cords, phones, and heating pads are the worst. Those are absolutely terrible. And it's not a low or high limit, but just a straight 60 hertz filter. So if you looked at a band of filters, a filter chart, you would see just this one little notch, as it were. It looks like just one little column or line, and that's the 60 hertz filter. And we use that because our electric outlets are they are at 60 hertz. So this is kind of what 60 hertz looks like. It can be a lot darker too, depending on what system you're using. So the notch filter also controls the rate of the input signal's fall. We don't want to use the notch filter unless we absolutely have to, but just about everywhere I've worked and done clinicals, they all use the notch filter. Here are some EEG waveforms. You're pretty familiar with them now. I prefer to remember them as D-tab, starting with the lowest and going to the fastest, but this is a decent representation of what those generally look like. So physiological artifact can often more likely be eliminated on the patient first. That's really what you want to do is get it right on the patient, because when you get it right on the patient, you're not going to have to do much else to fix it. And if you get it right the first time when you originally hook them up, now that's going to be even better for you and the patient, because you don't have to bother them so much. Alright, that was a little longer than I wanted it to be, but we've talked a lot about frequencies and stuff like that, but I wanted to have one at least just on filters. Alright, bye-bye.